Yes, and dear audience, I will speak mainly about history and relation of, let me say, politics and big science. Nevertheless, I start with a very few transparencies which somehow explain, not explain, but which give a hint why neutrons are why we like them so much. Okay. Verstanden. What you see here, by the way, is Cherenkov light. Cherenkov light, that is something very beautiful, and it shows you also how we can handle, let me say, nuclear activities. Cherenkov light happens if charged particles move faster than the speed of sound in the medium, here in water. So you have a beast which is very highly radioactive, in this case, a spent fuel element, and you can look at, you can see on it with your eyes. Why? Because water is so kind to have a gap for visible light, but have no gap. That means stops all radiation which is outside of the range of visible light. By the way, this is why life exists on Earth, because only the visible light comes to Earth and most of the other radiation, which is very harmful, is stopped. Okay. Next slide. This doesn't work. Why not? Okay, now it works. Here's the outline of my talk. On the neutrons for what? Very brief. Then the early history longer. Europe is leading in science with neutrons also takes some time. And at the very end, we are discussing where are we going with neutron sources. Good. Just a reminder, you see here an atom, and the dimension of an atom is 0.1 nanometer or 1 angstrom. The neutrons, once freed, they have only a diameter of 2.10 to minus 15 meter. So they are roughly 100,000 times smaller. And they are neutral, and therefore they pass easily all kind of matter, because in first or zeroth order, they don't interact with the charge of the protons and the electrons, but only with the nucleus. Okay. Once they are freed, they have a finite lifetime, which at the end is very long, some 14 minutes. And neutrons are wave. And this is very important. And because they are wave, and because they have a wavelength in the order of atoms, we can make visible atoms. So we can say, where are the atoms? Because neutrons have an energy typically of the energy of, let me say, our surrounding, namely, in my terms, in some 20, 25 milli-eV, they can easily detect the movement of our surrounding matter. Okay, so they tell us how move atoms or molecules. Because neutrons have a spin, so they have a magnetic moment, they have a compass needle. Because they have this compass needle, they can interact with the spin, with the magnetic moment of matter. Now, whatever is magnetic, I will not cite here now iron, but let's think about the magnetic disk in your computer. They can detect the magnetic moments of such things. So what is atomic molecular magnetism? Neutron science or neutron scattering is the most powerful method to test magnetism. Another one also very famous is nuclear magnetic resonance. Good. But neutrons are not only wave, they have also particle character, and as such, they interact as such, they create nuclear reactions. So if a neutron hits matter, it is not only scattered, diffracted, but sometimes also the neutron is eaten. Eaten means really a nuclear reaction happens, it disappears and something else appears. Okay, just a very few samples. This is once again to explain you in case, because neutrons are wave, they interfere with ordered buoys, as you see here with the water wave, and translated to our today topic, this ordered buoys is a crystalline order of whatever kind of matter. And the dominating equation, which dominates everything that we are doing, is a Bragg equation, namely the scattering angle is proportional to the distance of the regular arrangement of the atoms. and depends on the wavelength lambda. And because lambda is in the order of d, the distance of atoms, we can see so nicely the distance of atoms. No? This is Abel principle. Good. One example, you put a lithium-ion battery. By the way, this example stems from a Tesla battery, which is some 4 centimeters high and a centimeter in diameter. And you get this diffractogram, and the diffractogram tells you what is in the battery. Completely non-destructive. No? And you can do so during the battery is operating, charging, discharging, a used one, a fresh one, and so on. And you see the cathode, and you see the anode, and we can follow how these peaks evolve over charging, discharging, and then the engineer really learns on the atomic level what happens within his battery, completely non-destructive. Atoms tell us how atoms are moving. What is showing here? A plot of frequency and reduced wave vector. Reduced wave vector is nothing else than the scattering angle. This will be explained later on. And frequency just means the energy change between the incoming and the scattered neutrons. So we measure an energy change as function of angle, and the outcome is then something like this, namely the phonon dispersion relation. And the phonon dispersion relation is the holy grail of, let me say, what is the dynamics of atoms. And typically energies are here written in frequencies, but if I go back to my megahertz, millievolt units, then 1 terahertz is 4 millieV. So we are moving in the range of energies which are typically for room temperature a little bit higher. So how do the atoms move? How do we learn about magnetism? Because the neutron spin interacts with the magnetic spin, we can see the order of spins. And what you see here is magnesium silicide, which forms this chromium lattice at 25 Kelvin and under gradient of a magnetic field. What you see here is a cartoon. The cartoon comes from a diffraction picture, which I show you here. And once again, here's the two axes, Qy and Qx are just angles up and down. And what you see is a small angle neutron scattering result. And the peaks, intensities, those correctly interpreted give you just the picture which is underlying. So we learn where are the atomic spins, and we also can learn how they move. One keyword, fermions, might be new kind of order for storing information. Good. I come to things which you will not hear, let me say, in the next few hours, but which are also very important for using neutrons, namely that neutrons can do nuclear reactions. And I have shown here one. So a thermal neutron hits silicon, normal silicon, single crystal if possible. And with 2% abundance, we have one isotope, namely silicon 30. And this catches the neutron and transmutes to phosphorus, phosphorus 31, stable isotope after 2.6 hours of decay time. So the physicist does what the chemist can't do. We change elements. We make of lead gold. Here we make phosphorus of silicon. And phosphorus is the ideal dopant for n-doping silicon that it becomes semiconducting. Below you see the huge advantage of this very homogeneous doping. Green is the resistance over a certain distance on such, also thermal, sorry, I have to go back, or the resistance or the inverse is a conductance. So very homogeneously doped by neutron transmutation, and above red, same area, is a variation of the conductivity or resistance if you dope it conventionally by ion bombardment and so on. So the more homogeneous, the better. These things are highly needed nowadays. Annual need of 150 tons for electromobility and DC high voltage current transportation. So a revolution in energy supply strongly depends on this homogeneously doped silicon. Nuclear reaction does not only mean that we create stable isotopes, mainly we create non-stable radioactive isotopes. And one of those might be lutetium-177. Lutetium-177 is urgently needed for curing up to now for curing cancers, and kind of cancers which we can't cure, let me say, some 7 or 8 years ago. You see here one very, let me say, specular example. On the very left, a patient with a prostata carcinoma. No? So everything which is black is a carcinoma, a melanoma. So this patient will die within 2 months or so with a lot of pain. On the very right side, you see this patient after roughly 1 year, and he got 4 doses of lutetium-177. And the doses is, let me say, 1/5 of a normal irradiation dose. So he gets low doses, and you see that this patient is completely cured. Don't worry about the black parts here in the liver or in the or here in the Speicheldrüse. This is normal, and this does not harm. So this is a unique way to cure patients thanks to radioisotopes created by neutron capture. Let me come to the very last example. Neutrons are light, as I said in the beginning. They penetrate easily matter, as we heard already. For instance, a 10 centimeter aluminum, only 40% are absorbed and 60% are going through or scattered. So 10 centimeter of aluminum is almost completely transparent for neutrons. So take a motor engine, because I'm coming from Munich, it's a BMW 4-cylinder engine. You put it into a neutron beam, and what happens? I hope you can see this movie. You see on a millisecond time scale by radiography how the pistons are moving, and you see one particular thing, namely the oil jet, who is cooling the cylinders. Without this oil jet, your motor would crack immediately after a few, less than a minute, due to too much heating. Good. This is enough for why we need neutrons. Hopefully you are a little bit convinced. Let me come now to my main topic, the early history of science with neutrons. We should be aware that everything started within Second World War. Neutron was already known, Chadwick. It was known that neutrons have wave character some 2-3 years later, but there were no decent neutron sources. Decent neutron sources became available during Second World War because United States and other nations, also Germany, had interest to build an atomic bomb. But for the atomic bomb, you needed materials which produces enough neutrons. And the Americans, I would say nowadays, fortunately, were the only one which were successful. Chicago Pile in 1952 or so was the first reactor where enough purified uranium was available to create a continuous source of neutrons. Following this history, after Second World War, the hydrogen bomb was developed, and the worldwide public realized how terrible these atomic bombs are. Eisenhower, at that time, in the early 50s, was president of the United States, and he had the idea we have to do something to show that nuclear power is not only good for atomic bombs, but is a huge chance for peaceful use. So he gave the UN the famous UN speech on 8th of December 1953, where he said, "Atoms for peace." As a follow-up of the International Conference on the Peaceful Uses of Atomic Energy in Geneva, which followed then in Switzerland in 1955, it brought together world leaders to discuss peace and aimed to reduce international tensions. It led to the foundation of the International Atomic Energy Association, IAEA, which is a sub-organization of the UNO, as a sub-organization of the UN to implement the Atoms for Peace program, opening up research nuclear research to civilians and countries that had not previously possessed nuclear technology. And IAEA was created in July 1957. This cleared the ways for peaceful use of nuclear technology in non-weapon states, like Germany and other countries, not France and United Kingdom. I will come back to them later on. But let's first take this example, what was possible after Second World War, where the young Federal Republic was forbidden to have any nuclear technology. And this being forbidden to have any nuclear technology was then skipped due to this program of Atoms for Peace. What happened? A research reactor for the Technische Hochschule Munich. At this time, this was the name of the technical university. And in June 1956, the Bavarian Minister President, please pay attention, not the minister, not Adenauer, not the president, the Chancellor of the Federal Republic, but the Bavarian Minister President made a cabinet decision to have the first nuclear facility within Germany. So June 6. Only a few days, 11th of June, a young famous professor, not at that time, but he became famous, was sent to America with this simple letter you see here. By the way, I will make available transparency later on, so you can read them very carefully. This is really the original, a copy of the original letter, with which Heinz Meyer-Leibniz was sent to the United States, please buy a reactor. So simple, only 10 days later, and I think 1 week later, he traveled to the United States. And 1 year later, you see here the Bavarian Prime Minister, Högner, unpacked the first fuel element in September 1957. September 1957. So the first criticality can't be very far away. And this you see on this picture. The atom egg has become, in a certain way, a symbol for nuclear technology, mainly due to its, let me say, also architectural beauty. So, in this time, it took 2 months for a design of a neutron source. It took 11 months for construction, and the first criticality was in October 1957. To take up the mood of this time, I have gathered a few pictures. So what you see here on the right is the news of the German Agriculture Society. And this is not a fake, this is really as it was. No? Horses here on the fields, on the green fields of Garching, and just here the construction, which just took 11 months. This is the Cherenkov light of this kind of very small reactor. And the shape of the atom egg even came into fashion newspapers. I think this is from the German fashion newspaper Burda, but I'm not quite sure. And the reactor also serves in the coat of arms of the, at that time, still village, nowadays city of Garching. And due to this reactor, Garching has become renowned worldwide. Very few figures only of this reactor. These figures are important because we will learn other figures later on. So keep in mind, everything started with 1 megawatt thermal power. At the very end, it was upgraded to 4 megawatt thermal power. Everything started with low enriched uranium, 20% enrichment. It ended up with higher enrichment. The flux was increased from 6 times 10 to 12 neutrons per centimeter square and second to something 8 times 10 to 13. That means almost more than a factor of 10 more. Okay, and this reactor was decommissioned in 2000, and later on you will learn why it was decommissioned. More important for you is really this person here. This young professor sent to the United States and came back with a reactor. I think his travel took some 10 days. Heinz Meyer-Leibniz, just a second. So, Heinz Meyer-Leibniz had the motto, do something new. Please keep this in mind. Imagine, in 1956, the Americans were absolutely dominating neutron science because they had beautiful neutron sources which they inherited from the nuclear weapon program. So for Heinz Meyer-Leibniz, it was clear, if we want to compete, we have to do something completely different. And he did completely different. And I will show you how he did. And therefore, Heinz Meyer-Leibniz became father of research with neutrons in Europe. Good. What did he knew? Here I have noted at least 10 things which have been invented at this atom egg. Please imagine the following. And I will show you later on. In almost all countries, nuclear research reactors were built, but most of them were only used for two purposes, namely developing nuclear technology for energy and for material testing. Heinz Meyer-Leibniz said, I am not interested in nuclear technology for energy. That is not our matter. I'm university. We have to do something completely new. Most famous thing you all know are the Newton guides. His student Springer invented those, and Steichele built the first Newton guides. Newton guides where you guide neutron wherever you want, almost without losses, which is absolutely crucial for what we are doing today. You know neutron cross-sections. The first and most precise neutron, not the most precise, that's not correct, but the first cross-section have been measured by Köster and Rauch. Köster at FM2 and Rauch later on at the small research reactor at Vienna, which is very similar to the FM2. High precision nuclear spectroscopy invented by Fonigidi. All these people, by the way, all these people are pupils from Heinz Meyer-Leibniz. So he's really behind this. High precision nuclear spectroscopy, then brought to, let me say, to an absolute dominance later on at Institut Laue-Langevin. The first time of flight diffraction instruments, Steichele. Today's spallation source wouldn't be thinkable without time of flight technologies. So Steichele was the first one to do so. By the way, very similar things happened at Dubna, which had a pulsed neutron source. Backscattering, invented by Heinz Meyer-Leibniz, but built by Berthold Ahlefeld, Jülich, and Anton Heidemann, TUM and Garching, and ILL. Ultra-cold neutrons. The most intense ultra-cold neutron source is still at ILL, and it is the Steichele turbine, which has been first built at Garching. Small angle scattering. The first huge small angle scattering have been built at Jülich and ILL, but the principle came from Schmatz, Springer, Shelton, Eberl, all pupils of Heinz Meyer-Leibniz. This old reactor has also a low temperature radiation facility, maybe not so important. Very important, tumor therapy with fast neutrons, and also neutron resonance spin echo. The neutron spin echo has been invented by Mesai at ILL. Okay, so these are examples. The development of neutron methods at the atomic egg laid the foundation of the leadership of Newton in research with neutrons. The atom egg was not the only small, let me say, small reactor which was built at that time. Other reactors of very much the same times were built at Lissabon, in Portugal, at Villingen PSI, in the Paul Scherrer Institute in Switzerland, or at the Technical University of Delft in the Netherlands, at Geesthacht in Germany. And of those reactors, still the one in Lissabon and the one in TU Delft is running. And in particular, the TU Delft reactor has very modern instrumentation nowadays. And the picture you see here, both are coming from the TU Delft reactor, which operates today at 2 megawatt and has a flux roughly below 10 to 14 newtons per centimeter square in second. Something which is not very present in our mind is that Europe was divided at that time in East and West, and nowadays still is, unfortunately. As Eisenhower promoted atoms for peace, same happens in the Soviet Union at that time. And please have a look to the date which is marked here, December 16th, 1957. That means only 16 days after first criticality of the old atom egg, the first criticality of a research reactor in the GDR, so that means former East Germany, was inaugurated, and this is a reactor which was built by Soviet Union. Have also a look to the values here. This was already a 10 megawatt reactor. I have not noted here, and was already a reactor moderated with heavy water instead light water. And as we will see later on, heavy water is much better suited for moderating neutrons than light water. So this was in a certain way a reactor which was superior to what happened at the same time in West. You didn't hear so much about science from this reactor, despite it was a reactor which was in principle better suited for science with neutrons than those which were built in the West at the same time. And this is mainly because not only reactors are important, not only fluxes, people are important. In East Germany, there was no one who said we have to do something completely new, different than what was known up to this time. So people are crucial. I have to come to the two states, namely France and the United Kingdom. Both are weapon states in terms of the non-proliferation treaty. And of course, both countries had the possibility, were allowed and did so, build research reactors much earlier than the year 57. But they did build them mainly for their own weapon programs or for promoting nuclear power plants. So most of these reactors were just MTR, or the material test reactors, or on the way to develop nuclear energy. But let me pick out three of this list of French reactors. EL2 and EL3, both in Saclay. Inauguration of the first neutrons 52 and 57. Stopped in the 60s and late 80s. And at the very end, the most new one, research reactor in France, Orphée. First neutrons 1980. EL2 and EL3 hardly were used for science with neutron. Here you see a picture of EL2, and you don't see so much, let me say, instruments outside of the pile. Nevertheless, EL2 is important for the, let me say, the development of neutron science, because to my knowledge, to my best knowledge, there was the first cold source. Okay, I didn't introduce techniques how we shift the wavelengths for using neutrons, but you certainly may have heard of it. In a cold source, typically at 25 Kelvin, either D2 or H2, we moderate the neutrons from a wavelength of typically, let me say, 0.1 nanometer to wavelengths in the order of 0.6 to 1 nanometer. With other words, we shift the wavelengths by an order of magnitude. And cold neutrons and instrumentation at cold neutrons are extremely important for our kind of science. Also, this reactor, first neutron guides have been built after they have been invented at Garching. And of course, I have to show a picture of Orphée, the reactor which belongs to the Laboratoire Léon Brioin. First neutrons in 1980 and stopped, I think, in December 2019. I show you this picture just to make the difference. Here you see almost nothing around the pile. Here everything is completely crowded, and this is positive being crowded. With other words, full of scattering instruments. I will come back to Orphée later on. Let me say a few words about the United Kingdom. The United Kingdom, once again, is an atomic weapon state. The Atomic Energy Research Establishment, the area, was the main center for atomic energy research from 46 to 1990s. And of course, there was an early availability of research reactor, but mainly for the development of nuclear energy applications and material testing and radioisotopes. Two of those many reactors that it built at that time were Dido and Pluto. Maybe some of you have already heard these two names. First neutrons in 56 and 57. Already 26 megawatt, heavy water moderated. So think about the atom egg also went into operation 57, but the Germans were only allowed to have light water moderator, so much less flux. But from a reactor with much less flux, thanks to personalities, a huge development for Newton science. Dido and Pluto in the United Kingdom were not so famous for developing Newton science, but mainly for material testing. And both were shut down in 1990. I will come back to, let me say, the richdom of the United Kingdom in Newton science, but they did it in a completely different way. We will learn later on. One thing has to be mentioned. Dido, also closed in the United Kingdom, where the type of reactor were exported to Jülich, Forschungszentrum Jülich in Germany, to Riese National Lab, and to Ansdor in Australia. And these three countries or sites did plenty of Newton science with this kind of reactors. Okay, so you see similar or same reactor, completely different usage. Okay, so now I have to come to Europe is leading in science with neutrons. Up to now, we are not yet leading. That means late 60s. So what happened? In January 22nd, in 1963, Adenauer and Charles de Gaulle, Konrad Adenauer and Charles de Gaulle, made this famous treaty, and the French-German know very well, the Entente Franco-Allemande. And within this Entente, the LSE treaty and the Entente Franco-Allemande, there was one very important thing. So Adenauer and de Gaulle, they were intelligent, clever guys. They did know after 100 years of deep enemies between Germany and France, they had to do something to create friendship. And they had one idea. We have to have projects where both nations are working together on a cultural level to bring the cultures together. Culture makes peace. Okay, and science is part of culture. And the idea was make science in the service of diplomacy. So create something unique. This was in 63. 2-3 years, almost nothing happened. Charles de Gaulle and Konrad Adenauer were very disappointed about the community, let me say the scientific community in France and Germany, said they didn't bring up a huge project. But then came Jules Horowitz, Néel, Berthollet, and Heinz Meyer-Leibniz, so French and German famous scientists, and they had this idea, let's create a decent neutron source. Decent. So this was the establishment of the Max von Laue Paul Langevin Institute, ILL, by Heinz Meyer-Leibniz and Jules Horowitz. And it took just 5 years to create, to build, and first neutrons. Heinz Meyer-Leibniz could implement at the ILL a tailor-made neutron source with the highest neutron flux, and everything he had learned in the Garching atom egg he brought to Grenoble. Together, important, together with his numerous students. So let me explain this a little bit more. You see here's a nice picture, ILL and also the ESF. So with the ILL, Europe has taken the lead in research with neutrons to this day. Very important. Why lead? First, because this perfect heavy water moderated and cooled reactor has had cold source, hot source, ultra cold source, neutron guides, and all the instrumentation we have seen before, which was developed mainly at FM2, but also in France and Jülich. Okay. So intensity and again, personalities which brought the right science. Here a few figures to the ILL. Also creation of this Franco-German cultural identity through a joint large-scale research institution, named the Institut Laue-Langevin. Heinz Meyer-Leibniz, Louis Néel, also Nobel Prize winner at Grenoble, therefore cite Grenoble, by the way. Jules Horowitz, Robert Dautrey, Félix Berthollet took the initiative of the high flux neutron source in competition with the dominance of the USA. It was very clear, we have to make something to be better than the United States in the field of neutron research. There were colloquia in Grenoble and Munich. Heinz Meyer-Leibniz was professor at Munich, came from Munich. The idea of cold source a la EL3, and here I added Havel. I am not quite sure, but I think in one of the Havel reactors there was also already a cold source. So the cold source, which is so essential for the success of ILL, has two fathers, namely the French EL3 and most probably also Havel. Contract signing was 67. The first founding director was Heinz Meyer-Leibniz, so he moved for 5 years from Munich to Grenoble. Bertrand Jacquot was the French deputy director. And very important, where are the United Kingdom? Where is the United Kingdom? At the beginning, they say strictly, no, we don't want to. But then they saw something is growing up, and already in 1970, the United Kingdom joins ILL. And now think about who signs the contract. You will laugh maybe. Thanks to Science Secretary Margaret Thatcher. She signs the contract for joining United Kingdom to ILL. Okay, during these 5 years of building, the first scientists were situated here at Garching at the Walter Meissner Institute. And later on, then in 72, they moved to Grenoble. First criticality, as I told you, wait a moment, this is not completely true. This was not in 72, it was in late 71. So here I made a mistake. Very important, after the 5 years of directorate by Heinz Meyer-Leibniz, he went back to Germany, became head of the German Science for DFG, German Science Foundation. Rudolf Mösbauer, his most famous pupil, became director of ILL. Why do I mention this name? He is part of the big success because he introduced something about which Meyer-Leibniz had not thought about, and neither Jules Horowitz, namely to create a user facility. So the ILL is not there that some very smart, intelligent scientists at the ILL, paid by Germany, United Kingdom, and France, do their own science. ILL is there to serve best science in the world. You get access to the instrumentation of ILL in only scientific competition. This scientific competition is part of creating excellence. Okay, and in August 21, the ILL celebrated 50 years of Newton. So now we know this was in August 71 when the first criticality appeared. But user program started in 72. So founded in 67, the ILL produced the first Newtons, here it is, and published its first scientific results a couple of months later. I like this picture very much. It has a message, this picture. Mutual fertilization of science and diplomacy still applies today. The picture you see here is a renewal of the Élysée Treaty, which is the origin of the ILL in 2019. And I think we as scientists should take first opportunities of, let me say, diplomatic opportunities. Good. There was a huge knowledge transfer to ILL from Saclay, also partly from CEA Grenoble, from Garching, and from Jülich. So the nuclear technology really clearly for ILL came from CEA, Horowitz. Diffraction and magnetism clearly comes from Néel, Horowitz, Dautré, Berthaud. There were some very famous German directors. One of the agreements of this international society ILL is that the directors should be not from France, because France is already the sitting country. So don't be astonished that only one French director was there during the up to today. So Heinz Meyer-Leibniz, Mösbauer, Springer, Armbruster, Gläser, Scherm, Dubers, and also recently Schober. He learned a lot of things also here in Munich. The user facility, and this idea came from Mösbauer, Newton guides. Yeah, and I just mentioned once again the UCN, still the most intense UCN at ILL. First turbine was built here at Garching. Good. So what happened in France at that time? There was, of course, knowledge transfer back from ILL to French national sources. The Orphée, the reactor of the Laboratoire Léon Briand, has produced its first neutrons in 1980. So that means some 8 years after the first neutrons at ILL. What the French community, what did they learn from ILL? They learned from ILL, yeah, the interest in neutron scattering. And there were now so many French users that the ILL couldn't serve any longer the French needs. Therefore, they needed an own national source. And they needed a decent national source, and a decent national source only dedicated to neutron science. So we move completely away from these multiple purpose reactors. We move to what the ILL created first, a dedicated source only for neutron science. The layout in a certain way is very similar to the ILL. The power is less, in the order of 20. Yeah, I forgot to note it here. I think 26, is this correct? 26 megawatt was of him, maybe I'm wrong. But very important, H2O cooled. So this is brokers vis-a-vis ILL, not D2O cooled, but H2O cold, but heavy water moderated, cold source, hot source, and hot source means always really hot source. So we shift neutrons to shorter wavelengths and to longer wavelengths. 50 or some 25 instruments, a user facility, open access, even as a national source, international usage was there because the French National Neutron Society was interested in being competitive and to have the best, let me say, scientists at their place. So huge success, very similar in technology like LL, but in flux a little bit less in the order of 3 to 4 times 10 to 15 newtons per centimeter square and second in the moderator. I didn't mention what is the flux of the ILL reactor. It is 1.3 times 10 to 15 newtons per centimeter square and second. So you see almost 2 orders of higher of the very early beginning small reactors. Good. This is a decent French national source, closed recently in late 2019. We have to come back to United Kingdom. Closing Dido and Pluto, the only reactor, let me say, useful for Newton science, didn't mean they were not interested in Newton science, not at all. The British did something else. On the Harvard side, they had an accelerator for nuclear physics, which was no longer interesting for nuclear physics itself, and they built a spallation source. It is not the first spallation source. The first spallation source was built at Los Alamos, as far as I know, and at Argonne National Lab, but it was the first European, and still is the first European, no, we have Switzerland. It was the first European spallation source. Nowadays, this spallation source has 2 targets. It has a repetition rate of 50 Hertz. Target station 1 gets 4 beams and out of 4 pulses, and 1 pulse goes to the target station number 2. It is a short pulse neutron source. It has in the order of some, they are not marked here, more than 25 instruments for user operation, similar to LLB, completely open to user facility. The United Kingdom nowadays has the largest neutron scattering community in Europe, bigger than the one in France and in Germany. They have some 2,000 visitors per year and publications in the order of 480 or so. The ILL nowadays has at least 2,000, and to compare with, has also 2,000 visitors per year, roughly some 600 publications per year. Okay, so we have heard about the national source in France. We have heard about the national source in United Kingdom, which is a spallation source. And I have to come back to my home city or homeland. And this is now the Heinz Meyer-Leitman neutron source in the heart of a university campus. You see small part of the university campus, you see red, with the red lines. What is the FM2? So a few figures. In 81, there was a first presentation here at Garching of upgrading the atom egg. After 57, first Newtons, so 81, pupils of Professor Glaser thought about upgrading the FRM. Parallel in Germany, there were severe thoughts about building a large German spallation source. This project failed due to money in 85. In 1996, there was a groundbreaking ceremony for building now not an upgrade of the old FRM2 egg, but a new reactor, because soon it was realized that upgrading didn't make sense. So construction started in 96. In 98, that means 2 years later, we got a red-green government. And as you all know, red-green is not very much in favor of nuclear. And the consequence was that from 2001, there was a 2-year construction stop. But finally, you know, Federal Republic has also some rationales. The Green Federal Environment Minister agreed to sign the permission to operate FM2, and FM2 became critical in March 2004. So 96 to 2004, that makes 8 years of construction, where 2 years were political waiting time. Not so bad, but still you see time increases to build something compared to the very first neutron sources. But only 1 year later, the user services started with 10 instruments. And I think this is something we should keep in mind. And because the research reactor at Forschungszentrum Jülich, Dido, imported from United Kingdom, closed in 2006, all not all, but most of the neutron activities from the Forschungszentrum Jülich moved to FM2. Initially 5 instruments, but in 2011, altogether 13 instruments either moved from Jülich or were built completely new by Jülich here at the Forschungsreaktor. So you see something. The reactor was built by Bavaria, but later on, after Federal Republic realized this is a beautiful source, they joined, and the Federal Republic joined at least in financing this national source. And we had a bundling of German research with neutrons at the Heinz-Meyer-Leibniz Center. Bundling means that also G-Start stopped in 2010 its research reactor and came also to MLZ. The other German research reactor, namely in Berlin, did join initially, but after two years, so 2011 to 2013, they left this consortium and decided to close completely the reactor at Berlin and to step out of neutron scattering. Good. Yeah, what did we learn? The creation of a large-scale facility is always the result of subtle interaction between politics and science. You saw it at ILL. You see it also at Heinz-Meyer-Leibniz neutron source. Personalities are crucial to pick up political sociality opportunities. In the particular case of the Munich research reactor, local Bavarian government beats federal government. Also part of politics. At least I have to show you one modern design of a research reactor. And very important is that in the moderator already the neutrons are shifted to cold neutrons, to hot neutrons. In a few years, there will be an ultra-cold neutron source, which hopefully is then the most intense on the world. With some luck, it will have a factor of 10 to 100 more intensity than the UCN source at ILL, but let's see, this has to be proved. And there is also something else, which I didn't mention too much now. Here is this converter facility. So this reactor converts thermal neutrons in fission neutrons. And with these fission neutrons, you do either material science or atomography, in this case with fission neutrons, which have completely different cross-section, or you do something for health, namely hadron cancer therapy. So you irradiate cancers with neutrons, which can be done quite successfully, but which remains a niche product because these neutron sources are not always available. Good. This is the most modern neutron source with broadest application spectrum. So with ILL, we had a shift to have only a dedicated neutron source for science. At FM2, this is not completely true. There is a way back. Why? Because everyone was aware in the late 90s or beginning 2000s, this will be the last reactor in Germany. So it has really a multi-purpose character. Good. So you see here the neutron guide hall. The second one is under construction and will be inaugurated hopefully very soon. It's a national German neutron source. It has approximately 500 employees. Compared to ILL, some 600 altogether, some 1,000 or a little bit more scientific visits from user each year, some 350 publications per year, more, and this is a very important figure here, more than 200 doctoral students use MLZ every year. And this comes mainly because this reactor is also installed on a large university campus. So, today, 27 instruments in operation, 5 more are under construction. They will be mainly located in the new Guide Hall East. MLZ is a model case for policity-inspired networking of university and large-scale facilities. And this picture is just to impress you that it is very full. This is the experimental hall. The Neutron Guide Hall looks very similar. And on the left, you see a lot of universities. All these German universities or research groups have built the instruments at FM2. So this is now a new principle. Heinz Meyer-Leibniz introduced the user facility. We introduced something like, let me say, in-kind contribution. And this idea of in-kind contribution is now a main idea of the ESS spallation source. So expert groups, so future users, build the instruments and take responsibility for the instruments. This responsibility might only be they build the instrument, give it to the large-scale facility, or they continue to operate. Let's see how it evolves at the ESS. This picture is important to understand, let me say, what flux means. We have in worldwide 3 reactors which very high flux in the order of 10 to 15. By the way, FM2 has 8 times 10 to 14, ILL 1.3 times 10 to 15, and Oak Ridge similar. They have very different building years, 65 to 2004, or yeah. They have very different power, but at the end they have all the same size, same Newton flux. This shows you the progress in constructing neutron sources by fission reactors. So we are, where are we going with neutron science sources? This picture here on the right is in a certain way very disillusionating. Here are years of first neutrons. You see Chadwick, no? Almost 0 is a logarithmic scale, peak neutron flux. And here we are in the order of 10 to 50 in the moderator. And red are these fission reactors. Blue are pulse sources, mainly spallation sources, but not only pulse sources. And in the pulse, they get a factor of 10 to a little bit more, not 100, but more than 10, more flux, but only in the pulse. Time average, this blue line lies at maximum here on this red line. That means over 16 years, the time averaged flux in the moderator is in the order of 10 to 15 newtons per centimeter square in second. Why so? It doesn't matter, spallation source or fission reactor, there's a technical limit, and the technical limit is really evaporating heat. And we all want to operate safe nuclear facilities. So where is the progress? Is there no progress in 60 years? There's a lot of progress. Read my next line here. Not intensity, but the measurable signal. That means the peak to background in what you measure, this ratio, in the detector, not on your sample, in the detector finally, is really decisive for, let me say, the best neutron instrumentation. So peak to background ratio in the detector. And this measurable signal increases in the last 60 years, every 10 years by a factor of 10. So the usable measurable signal really every 10 years we increase 1 order of magnitude. And this comes to progress in moderation, progress in guiding neutrons and neutron optics, progress in detectors, and also just installing detectors almost over 4 pi. Good. So there is real progress. What will bring us the future? Of course, European spallation source. The picture you see here is from October 21, so very recently, and you see that the civil building is almost ready. You see the large accelerator, which at its end is superconducting, target hall, neutron guide hall 1, and the second one, and the offices. Everything is very large. Here you see a sketch of the instrumentation as it will be when, let's look to time schedules. 2003, ESS design completed, 2009, decision for Lund, 2012, updated ESS design, 2018, reduction in scope, reduction in megawatt from 5 megawatt to 2 megawatt, 2018, official groundbreaking ceremony, 2022, civil buildings will be finished, namely end of December this year. Somewhere between 24 and 2024, 26, there will be the first beam on target. So this is in a certain way, I will not say disappointing, but this is reality. Building a spallation source is not only building civil works, but really taking accelerators, which are very complicated, difficult to handle, into operation. So this first beam on target will be much later than the civil engineering. And earliest in 28, start of, let me say, a decent user program. Shareholders now are many countries. Of course, the side countries, Denmark and Sweden, with a major contribution, then Germany, France and United Kingdom, and also countries like Czech Republic, Estonia, Hungary, Italy, Norway, Poland, Spain, and Switzerland. Let's speak about money. The total construction budget at the end of 27 is foreseen to be 3.7 billion euro. I was very fast with FM2. FM2 did cost 345 million euro. So almost an order of magnitude less. Okay, so a large scale facility is expensive, very expensive. So the increase from FM2 to ESS is a factor of 10. 2008 to 2025, 50 instruments in user service. ESS delivers capability, not capacity. This is important to understand. I will come back to it in a moment. About a factor of 10 or more, I will not say a factor of 100. I think this is exaggerating, but a factor of 10 and more superior to actual ILL. If I say actual ILL, I do not mean the ILL in total. I mean particular instruments. Those instruments where you can use peak flux, they will be in this order of 10 to 100 better than those at ILL. 10, I think, is a realistic figure. 100 is a dream. Good. Why ESS can do so? What you see here is brightness, so no longer flux. Brightness means flux per steradian and per wavelengths. You have now different units. And here you see time structure. So ILL is this line here on the base. This is 1.3 times 10 to 15 flux and translated into brilliance. And blue, this was the original design of the 5 megawatt pulse. So only over maximum 4 milliseconds. And then comes long time nothing. Repeating rate is 16 megahertz. So this was 5 megawatts. During this redesigning and changing the moderator, one went to 2 megawatt, but with better moderator. And this is how the ESS will be hopefully in 28. So a little bit less than the 5 megawatt with 2 megawatt, but still with a perfect pulse. So if you use, let me say, a certain width, and depends now what you can use of this pulse in the instrument, then you will be this factor of 10 or more better than a typical ILL instrument. Here you see also what short pulses, spallation pulses are doing. They have much shorter pulses. SNS at Oak Ridge. This is G-Park at Tokai, Japan. This is ISIS target station 2, and this is ISIS target station 1. Good. Original plant for 5 megawatts, redesigned to 2 megawatt with pancake-like moderator. So the advantage lies really in the advanced moderator design. And the measurable signal, I don't say any more brilliance intensity, I say measurable signal will be hopefully more than a factor of 10 better than certain instruments at ILL, those which you can compare. If you do tomography, you can't compare because there, in most cases, total intensity is decisive and not brightness in a short time. Good. Coming to the end, I should mention at least the two other reactors. PIC, something we like to forget in the East, is a research reactor in Russia now, intended to have 100 megawatt, maybe in 25. Its first neutrons were in 2019 with 100 kilowatt. In 2022, they expect to have 10 megawatt. And when will we start of user service? I will not speculate, certainly not so early. Important transfer of instruments from closed reactors at Helmholtz-Geestach and also from Orphée at LLB. And this is the planning of their neutron instrumentation. Something which looks even further into future is going a step back. 3.7 billion is expensive and maybe in the future too expensive. We have to think about other possibilities. And this thinking back means, why not being smart and small is beautiful? Build smaller neutron sources, which can be placed at university and very diverse, to create, let me say, a community. And this community then uses this, I would say, very performant national sources like SINCO in Switzerland, FM2 at Munich, or ISIS. And from there we use then the international facility, which still is ILL, and later on will be ESS. So there are two projects, one at Saclay, one at Jülich. Both use protons as accelerator, both are accelerator-based, but they do not use accelerators which have gigaevolt energies or near to gigaevolt. They work with moderated energies, namely the Sonata project at LLB with 20 MeV, the Jülich project with, I forgot to note it here, with some 70 megaevolt, but both protons. One has a beryllium target, the other one has a tantalum target. Tantalum goes into the direction of spallation, is not yet spallation, it's more stripping. As a beryllium target, it is only stripping. Both will have intensities, which I would say are a factor of 100, roughly, less than the most brilliant instruments at the national sources. The huge advantage of these sources is they are small, they are less complex, much cheaper in construction and operation. And now it comes, you can match target moderator reflector. You can match it to the particular purpose of one instrument. So each instrument will have its own matched target moderator reflector design. And here you gain again intensity. So maybe at the very end, we will see it is not a factor of 100, it's only a factor of 10 less flux than the decent instrument at these three national sources. Good. I have to come to the end, and I think this is my very last transparency. Already in 2016, S3, this European consideration of having neutron sources and light sources, published something of the future needs. So this is shown here on the right side. These are, let me say, instrument days available at ESS, here in Garching, at ISIS, at Paul Scherrer Institute, at ILL. First thing, in 2016, these wise people already have foreseen that the ILL will operate at least until 2030, so we are happy this happened. They did not foresee that ESS only becomes available from here. So this will start like this. Yeah, it is so. So these three here after 2030 will be, let me say, deliver capacity. ESS delivers capability. They deliver, let me say, the baseline for using this flagship facility. After closure of ILLs and national sources, PSI, ISIS, MLZ will deliver capacity, ESS capability. Together, they guarantee the leading position of Europe in science with neutrons. And before stopping, I have to apologize one thing. Due to constraints in time, of course, I didn't say very much about this source here in Switzerland, which is also a spallation source, but not pulsed. So I beg your pardon that I didn't tell too much about this. Thank you very much for listening.
So thank you very much for this splendid presentation of neutron